Welcome to CLP 7525, Week 7. This week, our focus is on how variables travel together. We started this topic in MLM when we looked at time-varying covariates. We said the time-varying covariates could predict the peaks and valleys in a DV, the so-called residual variance. This can be done in MLM, and it's actually a bit easier in MLM. But there is another way to look at how two variables travel together that's not possible to do in MLM, and that is the idea of correlated intercepts and slopes. Instead of asking, does the non-systematic pattern of ups and downs associate, like we do with time-varying covariates, this asks, does the systematic linear and nonlinear change associate? There is another question we'll tackle this week, which is whether the association between two variables is not concurrent at the same time, but lagged. More precisely, cross-lagged. This can be a way to tease out potentially causal associations, something we've had to stay away from in every situation except the experimental design. This week, we'll also introduce another way of looking at the association among constructs over time, which is what we call multivariate growth models. I say introduce because we'll discuss these in detail next week, but we'll see that there are three variants. The first is a simple extension of what we'll already practice today, which is the associative model. It is the intercept and slope of one outcome associated with the intercept and slope of two or more other outcomes. But as you may remember from our multivariate class when we introduced higher order factors, when factors are correlated, sometimes this testifies to the existence of a higher order construct that unifies them. And so it is with growth models. If your height is growing and your weight is growing and your head circumference is growing, maybe these reflect a common process, in this case maturation in childhood or adolescence. And it's useful to identify and measure this common process. We'll see there are two ways of extracting these higher order growth processes: factor of curves and curve of factors. Now we're getting to the fun stuff. Our first set of analyses this week will address different ways of how two variables might travel together. The data are as follows. 100 participants with chronic pain were asked to report their bodily pain scores, higher equals worse, daily for 5 days. Participants were beginning a new exercise regime which, while designed over the long haul to help with pain, might increase pain in the short term. At each occasion, negative mood was also measured, higher equals worse mood. First, let's check the unconditional growth model. Let's just get a feeling for what the pattern in the data is. In this instance, preliminary work revealed that only linear change characterized the 5-day trajectory of pain. The next picture comes from Amos. We're not using Amos in this class, but conceptually I think the Amos path models, which is how you specify the models, helps to clarify what's going on. I'll do that a few times this week. So this is a traditional linear growth model. Things to remember: intercepts of the measured indicators and their residuals are fixed to 0. Homogeneous residual variance is set at all 5 occasions. The intercept and slope factor have estimated means or fixed effects and variances or random effects. The intercept is represented by a vector of 1s. The linear slope is defined by a vector of 0, 1, 2, 3, 4. So this is a simple linear growth model that you're well used to by now. Equally spaced linear slope and intercept, nothing special here. And focusing on the right, we see at the top that we have a fixed intercept of 49.2 and a fixed linear slope of 2.4. So every day, pain goes up by about 2.4 units. We see that the intercept and slope are not correlated in this example. Looking down, we see that we have significant random variance in both the pain intercept and slope. And we also have significant within-person variability, as defined by the significant homogeneous residual of 1.79. This model has a non-significant chi-square, near-perfect fit statistics, a non-significant and near-zero RMSEA, so it is a good model. And to get our plots, here are our usual tricks. The first ggplot will give us the fixed line for the total sample, and the second will give us the individualized spaghetti plot. Plotting the fixed mean and intercept, we see that the average trajectory is a very clear increase of over 2 points a day. And here is the spaghetti plot to convey the variability in intercept and slope. You can see that some slopes are steeper or flatter than others, and there's also a visual gestalt here that there's probably more variability in intercepts than there is in slopes, and that's actually interesting and will come into play again shortly. Implied by what I said in the introduction, there are several ways of seeing how two or more variables travel together. If we're interested in the correlated peaks and valleys, we're looking at time-varying covariates. If we're interested in whether two variables share intercept variance or similar rates of change over participants, we're interested in correlated growth models. And if we're just correlating the intercepts and slopes of two variables, this is called the associative model. And if we're predicting one variable's intercept and slope from another variable's intercept and slope, this has the cumbersome name of random intercepts and slopes predict random intercepts and slopes. And what we'll also see is that in SEM, there's no reason we can't look at both combined. So we'll do that too. First, let's implement the time-varying covariate in SEM.